All right, okay. Thank you, Kira. So it's my pleasure to introduce our speaker today, Dongruo Zhou. He's a third-year PhD student at UCLA, advised by Quanquan Gu. Before that, he did his bachelor's degree at Tsinghua University back in China, and he's also worked at the University of Virginia. So Dongruo has published amazing work in a number of different fields in optimization, bandits, and more recently, reinforcement learning theory. And today he's going to be telling us about his most recent results on nearly Minimax Optimal Reinforcement Learning for linear mixture MDPs. So with that, please, the floor is yours, Dongruo.
Okay, thanks for introduction, and it is my great pleasure to be invited by our series seminar. So today I'm going to introduce our recent work, nearly Minimax Optimal Reinforcement Learning for linear MDPs. This is joint work with my advisor, Quanquan Gu and Csaba Szepesvari from DeepMind and University of Alberta. So let's first begin with some background knowledge. So in this work, we are interested in the reinforcement learning algorithms on the decision-making problems. So in general, the reinforcement learning algorithms can be regarded as the algorithms where the agent would actively interact with some unknown environment by providing some actions towards the environment. And after the action taken, the environment would feedback the agent with some reward and to tell him, well, which would be the next state would he transit to. So reinforcement learning algorithms have been widely studied and used in many interesting application cases, including the Alpha Star working for the famous game StarCraft, and the autonomous driving algorithms working on the autonomous driving, and also some the intelligent assistant, just like Siri, from the dialogue system technology. So in this work, we are focusing on much more specific problem setting or the environment called the timing homogeneous episodic MDPs. So specifically, we can denote this timing homogeneous episodic MDP by the following tuples, where we use the A's to denote the state space, and the A to denote the action space, and the capital H to denote the lines of each episode. Here, this episode means like for each of the agent, once he starts from the initial state, after at most the capital H stages, he would end at the ending state and then begin the next episode and starting again as maybe the different initial state. And here we use the term timing homogeneous to suggest the following properties. Says at each different stage, the agent would face the different reward provided by the different reward functions determined by the environment, applying on the state and action pair. And also at each different stage, the transition dynamic the agent would face is different. So here we use the collection of the capital H number of the transition dynamics to denote the total transition dynamics during this episode. So the process for the online reinforcement learning algorithms running on these MDPs can be described as follows. Starting from the initial state, at the beginning of the case episode, the agent would first try to denote his own mapping as a capital H number of the collection of the individual policy, where each of the policy can be regarded as a stochastic or deterministic functions mapping from the state space A to the action space A. This policy tells the agent which action should he take and which action should he not. And in this work, for simplicity, we only consider the deterministic policy. And at the H stage, the agent first tries to select his own action at H stage based on his current state S. And after he takes this action, he would try to the environment would fit this agent with some reward and the next state. And here is a simple example of the general MDP here. So we need to use some notations to denote what would be the goal for the agent to achieve during these episodes. So in summary, this agent wants to maximize his unexpected future accumulated reward, which can be described by the Q function and the value function. And as you can see, we define this Q function as the expected future reward conditioned on the current policy and the state action the agent takes at the H stage. And this value function can be regarded as the Q function with the action induced by the policy. And to denote the optimality, we also use the optimal value function V star and the optimal Q function Q star simply as the supermin over all the possible policies over the Q function and the value function. So for this agent, his goal is to try to minimize the following measure called the regret, which can be regarded as the difference between the summation of the optimal value function and the summation of the true value function he takes at each episode. Okay, so in this work, we are interested in one very specific thing about the MDPs. That is, what are the statistical limits for the reinforcement learning to learn the general tabular MDPs? We want to measure the statistical limits by the measure regret we just introduced. So here, I try to summarize several nearly minimax optimum regret bounds obtained by the different algorithms for the general case tabular episodic MDPs. Here, the tabular term means that we want to access each of the transition dynamic and each of the reward function element by element, and it is natural for us to think about like if we are facing the tabular episodic MDPs, we might face on the cardinality of the state space A's and action space A. So in this table, we can see like depending on the different sub assumptions applied on the MDPs, like whether this MDP is homogeneous or whether the summation of the reward is bounded by the scale of capital H or 1. Several previous works have obtained different regret guarantee. As we can see, like comparing with the lower bound results, the optimal regrets have been achieved, especially for the dominant term, depending on the different assumptions. As we can see, so for the homogeneous setting and with the reward scale at H, the so-called statistical limit should be the H times square root of SAK, where the K is number of episodes. And for the inhomogeneous setting, the regret will be suffer additional square root of H factor, which would be the H to the power of 1.5 times square root of SAK. However, in this work, we are more interested in, again, a special class of MTPs called the MTPs with a low rank structure. Here, this low rank suggests that instead of learning the original MDPs element by element, which would cost us inevitably dependence on the state space cardinality A's and the action space cardinality A, on the low rank MDPs, we only need to learn the MDPs on the number of D features, which is often much smaller than the original state and action space cardinality. So this kind of special assumption might guarantee us sample efficient or a better statistical limits because we can utilize this special structure. Here are several representative low-ranked MDP classes, including the low Bellman rank MDP, the block MDP, the linear MDPs, and the recent proposed linear mixture MDPs. So our questions, actually our central questions in this work is that we want to know what are the statistical limits for the reinforcement learning on the low rank MDPs. In this work, we give this a partial answer by studying the linear mixture MDPs proposed and studied recently by Modi et al., Jia et al., Ariel et al., and Zhou et al. So we answer this question by providing nearly matching upper and lower regret bounds under some certain non-trivial parameter regime. Okay, so here ends the background introduction. So before we proceed to the linear mixture MDP setting, we first come to a much simpler linear bandit setting, which we call it a Heteroskedastic linear bandits. Although this setting is much simpler compared with the original MDP setting, we can still demonstrate the key idea and to show how how can we improve the previous results on this simpler setting. Okay. So here comes the Hydrostatistic linear bandit setting. So in this setting, at each step t, the agent would first receive the decision set dt provided by the environment, and then the agent would try to select his own action as the step t based on all his past observations, aka decided by some policies. And then this agent would try to observe the reward information provided by the environment. And what's more is that we assume that in this setting, the environment not only provides the agent the reward information, but also the variance information denoted by the sigma t here. Here, the assumption of the reward generation is that we assume the reward conditioned on the selected action will be the linear function of the selected action based on some unknown linear part mu star with some additional noise epsilon t. We assume like the magnitude of the epsilon t can be upper bounded by some constant r. But what's interesting is that we also assume like the variance of this noise can be upper bounded by some time varying constant sigma t square here. So that's why we call it a Hydrostatistic linear bandit, because we are facing on changing variance setting. So in this setting, our goal is still to try to minimize the regret, which can be regarded as the summation of the optimal expected reward and the summation of the true expected reward the agent receives.
Sorry, Dongruo, just a question.
Okay.
So I just have a question about this term, heteroskedastic. So here the adversary chooses, I guess, dt and sigma t jointly, but the noise variance does not depend on the actual choice of the learner. So it doesn't depend on AT. Is that right?
You mean this sigma t? Yeah, this sigma t does not depend on AT. We assume that this sigma t only depends on the time t here. That says for the different action here, they're always facing the same sigma t.
I see. And I suppose this setting is going to be somehow motivated by the MDP setup that you're gonna.
Yeah. I'll try to mention it later. The intuition why we want to study this is exactly motivated by the MDP setting, because they can regard it as more or less a complex version of the Heteroskedastic linear bandit. So we studied this simpler setting first.
I see. No, I just asked this because in my book, heteroskedasticity would mean that the noise variance actually depends on the action, but this is not the case here. The noise variance is just a function of t.
Yeah.
Or well, just a function of the history, I imagine.
Yeah. I guess from because I didn't introduce the MDP setting, but I guess once we learned how do we perform our algorithms on the MDP setting, I guess it may be possible for us to extend our bandits results to the more general setting, as you just mentioned.
Yeah. Right. Yeah. But I suppose dt and sigma t should still depend on like the past actions and the past reward realizations. Is that right?
At least in this linear bandit setting, we do not assume that. But later in the MDP setting, we may face a static complex setting, as you just mentioned. Maybe it depends on all the past observations. Yeah.
So just to clarify here, you write in point 3, observe the reward and the variance, but then you define sigma t as an upper bound in the variance.
Yeah, this sigma t is the variance of the noise here, just as we defined.
Not the upper bound on the variance.
Yeah, you can also call that the upper bound of variance, because our assumption says that the expectation of its second momentum can be upper bounded by this one. So this term can be an upper bound or the true bound. Both of them work.
Okay.
Okay, cool. So to try to minimize the regret over this heteroskedastic linear bandits problem, a key observation is that actually these linear bandits, if we just ignore the assumption, says that the variances of these noises can be upper bounded by some another constant instead of the R. If we just ignore this part, and then this problem becomes previously widely studied linear bandits problem, and we just select one of the representative algorithms called OFUL, proposed by Abbasi et al. To show what are the previous, maybe the optimal approach to solve this linear bandits problem. So the algorithm structure can be described as follows. So at the first step, the OFUL algorithms would try to compute the solution to the following ridge regression problem over all the predictor response pairs. Here, this predictor is all the past actions taken by the agent, and the reward is just the reward provided by the environment. And after the solution computed, the agent would try to construct the confidence set of the unknown linear part mu star by constructing an episode centering at the approximate solution hat mu t here with some confidence radius, which we call the hat beta t and the additional regulator term. And after the construction of the confidence set, the agent would try to estimate the so-called optimistic estimation of the different action, and then select the optimistic action by jointly maximizing this inner product between the action and the linear part approximation. Okay, so for this simple strategy, Abbasi et al. Have already shown, like, with hyperability, our constructed confidence set CT are indeed the confidence sets, which means that with hyperability, the unknown linear part indeed belongs to the joint of all the confidence sets. And to achieve this goal, actually, they only need to set the radius of the confidence set to be in the order R times square root of D. Well, to be recorded, the R is the magnitude of the noise. And after this confidence set construction, we can do the overall regret decomposition and bound the final regret by considering the following steps. In the first step, we can bound the regret as by the inner product between the difference of the optimistic linear part and the estimated linear part with the current action. And by one more step using the Cauchy-Schwarz inequality, we can further upper bound these bounds by the radius of the confidence sets, which consisting of the hat beta t here, and another uncertainty part, the AT with the matrix in norm here. And the final step is that we need to utilize the theorems here to suggest that actually the radius of the confidence set is in order R times square root of D, and we want to use another widely used lemma called elliptic potential lemma, which could bound the summation of the uncertainty part in order square root of dt. And to combine these two results suggest, like, actually the regret of OFUL is in order D times R times square root of T here. So we can see, like, in the OFUL achieves the regret in which is proportional to the R and times the square root of T. And a natural question is that since we have already considered a much more special case, so-called variance-dependent hydrostatic case, so we are interested in whether we can whether we can achieve a better noise, whether we can achieve a better regret if we consider the assumption more than the boundedness assumption. So so one key the key observation for us to obtain this tighter result is that we note that actually this R term comes from the regret is induced by the confidence radius here. So if we can somehow tighten the confidence radius, we can achieve the tighter regret. So this motivates us to study a tighter Bernstein type improved inequality for the vector valid martingales, which could provide us tighter results to bound the confidence radius. So our following theorem suggests that if we somehow consider the special homoscedastic case, suggests that each of the noise can be upper bounded by some identical constant sigma, and this sigma is always upper bounded by R. Then we just keep everything identical to the OFUL, and we can still have the following conclusion, which suggests that the first is that the confidence set constructed by the OFUL are still the confidence sets of the unknown linear part. And for the second thing is that under that special case, we can obtain a much tighter confidence radius, which is only in the order sigma times square root of D plus additional R here. So as you can see, this radius will be strictly smaller than the original confidence radius, since the dimension of the dimension D is always greater than 1, and the sigma is always upper bounded by R here. And some remarks are mentioned as follows. First, actually, although we only consider a case where the variance of this noise can be upper bounded by some sigma square, we can also extend it to the sub-exponential random variable case, where we replace the magnitude assumption by the sub-Gaussian assumption, and replace this one by the sub-exponential assumption, and our conclusion still holds. And our main proof strategy to show this improved result is to follow the induction proof strategy introduced first by Daniel et al. 2008 to bound a series of martingale different sequence, but again with the refined analysis which can tighten the original result from proportional to the R to the proportional to the sigma here. Okay. So we have already introduced algorithms where we can deal with the homoscedastic case with variance bounded assumption. However, how to deal with the original heteroskedastic linear bandits case? So in that case, we propose our algorithm called the weighted OFUL. So this weighted OFUL is very similar to the original OFUL algorithms, but only with following adjustment. First things, we compute the solution to the ridge regression over the weighted predictor response pairs instead of unweighted pairs. Here, the weights are determined by the inverse of the approximation of the upper bounds of the noise here. And this kind of strategy has also been considered by Latimer et al. And Krishnana and Cross et al. And Cross under the previous different settings. And the reason why we want to do this kind of reweighting strategy is that after this weighting, we can see like the weighted reward here, they enjoy the identical noise variance of the noise bound. Says we can apply our previous Titan Bernstein type inequality onto this transformed linear bandits problem. And the max operator here just simply try to just guarantee the division operation is always valid. And later we in the final stage we may try to select some very special alpha to guarantee like it would not affect the final result by a large degree. So after this solution, we compute we construct the confidence set of the mu star here again with the adjusted confidence radius and also with adjusted covariance matrix whose contexts are the weighted actions here. And then in the following, we still select the optimistic action identical to the FUL algorithm. Our theorem suggests that by following this kind of strategy and set this confidence radius in the order square root of d plus the r divided by the minimum of all the previous variance upper bound, our weighted FUL enjoys the following regret. It is worth noting that this regret is consisting of the two terms. The first term is in order r times square root of dt, and the second term is in order d times square root of summation of the variances. So we can see like compared with the previous result d times r times square root of t here, our regret is actually a strict improvement since the d is always greater than 1 and sigma t is always upper bounded by the r. And another interesting property is that actually our regret has always already climbed a nearly independence of the number of the rounds t results, where in the special parameter regime, where the summation of the variances is not so small, says it can be lower bounded by t times r squared divided by d. Okay, so here ends the result for the heterostatic linear Bandit setting. Do you have any questions?
No, I think it's perfectly clear.
Okay, cool. So just recall the weighted FUL strategy. We can bring this strategy to get our new RL algorithms for the linear mixture MDP setting. So before this starts, we need to introduce formally about the linear mixture MDP class. So we define the B-bounded linear mixture MDPs, where we assume that each of the reward function R is known for the simplicity. And what's more important is that we assume that there exists a bounded feature mapping, which is the feature map maps the state action state triple to the D-dimensional vector. And we need to get some normalization assumption on this phi here, where we'll use this notation phi of v, which can be regarded as a summation of the phi times the phi times any function v, and to do a summation over all the state space. And what's important is that we'll assume that there exists capital H number of the unknown linear parts theta h star, which whose norm is upper bounded by b, and we'll assume that for each stage, its dynamic can be parameterized as the linear function between the feature mapping phi and the unknown linear parts theta h star here. So we can take several examples to show what the linear mixture MDPs are, and actually this class is a big class which can include many interesting special cases. So the first thing is that for the tabular MDPs, actually we can regard it as very special linear mixture MDPs with the dimension d equals to the a squared times a, and we can take the feature mapping as an indicator function and the linear part of theta h star just as each element of the transition dynamic. And a recent studied model called the bilinear transition model proposed by Yang and Wang. And for this model, it can also be regarded as a special class of linear mixture MDPs, where they assume like the transition dynamic enjoys the bilinear formulation, and we can do a simple linear algebra transformation to construct our linear feature mapping and the unknown linear part based on their previous formulation. Okay, so we have already introduced the linear mixture MDP here, and we want to And we want to make the following key observations. The first observation is that the only unknown things in the linear mixture MDPs is the capital H number of the unknown linear parts. So that says if we want to learn the optimal policy or the optimal value function for on the some linear mixture MDPs, we only need to estimate the unknown linear parts in H star. And the second observation, which I think is much more important, is that we need to note the following key crucial equation suggests that for any function v, if we want to take the expectation of the v over the h transition dynamic, actually this kind of term can be parameterized by as a linear function of the unknown linear. Sorry, this is a typo. This by an unknown linear part in H star with the quantity phi of v we have defined before. So this simple observation motivates the so-called value target regression strategy first studied by Zhou et al. That suggests that if we already have enough number of the pairs which consisting of the state action, next state, and the estimated value function, well, this next state is generated by the according to the H transition dynamic, and then we can estimate this H star possibly by simply doing the regression over the predictor response pair phi of v and the value function here. Again, this strategy is valid due to the observation is that the expectation of this response is actually a linear function of the predictor. So by the knowledge from the linear bandits, we can estimate it and obtain a satisfiable regrets with hyperability. So the previous work Zhou et al. Proposed the algorithm UCL VTR algorithms, which can be regarded as the combination of the value target regression I just introduced at here and plus the OFUL strategy. So the main theorem of their work suggests that the UCL VTR algorithms enjoys the regret which is in the order d times h squared times square root of k. Okay, so now we can introduce the relationship between the heteroskedastic linear bandits and our going studied the linear mixture MDPs. And so the reason why we want to study this maybe at the first stage strange class of the heteroskedastic linear bandits, because this observation suggests that actually the predictor response pairs generated by the value target regression is actually can actually be regarded as the reward and action in the heteroskedastic linear bandits problem, because each of the variance of the value function applied on the next state can be different. So a natural thought to get an improved algorithm is that we can apply our previously weighted OFUL algorithms over the linear mixture MDPs based on the value target regression, value target regression structure. So here are the key steps for us to get better regret bound compared with UCL VTR. The first one is the use of the weighted OFUL algorithms, and the second one is the estimation to the variances of the value functions, which I will introduce later. And the last one is that to get strictly improved regret bound, we need to apply the well-known law of total variance lemma, which has been introduced and studied by Lattimore et al. And Azza et al. Okay, so here comes our UCL VTR plus algorithms, which is our main algorithm to learn the linear mixture MDPs. So at the H episode, the agent would first receive the initial state, and at the H stage, the agent would try to compute the solution to the regression over the weighted pairs. Here, this weight is again the inverse of the variance upper bound. But what's different from our linear mixture MDP setting to the original heteroskedastic linear bandit setting is that first thing First thing is that we do not know the exact variance of the value function because we do not know the underlying true transition dynamic. So that gives us another challenge is that we need to provide precise and computationally efficient enough estimation to the variance of the value function. And I will just leave it to the next slide. And I can just denote the variance bound here by the notion of the bar sigma kh here. And by the introduced weight, we can compute the solution by doing the regression over the weighted pairs. And after this computed solution, we can construct the confidence set, which is based on the predictor of phi of v applied on all the previous state action pair and weighted by the variance of the value function. And then we need to estimate each step of the value function according to the well-known Bellman equation. Here, we try to construct the estimated Q function based on the next step previously constructed value function by performing the optimistic construction principle by regarding this Q function as the summation of the current step reward function with optimistic linear function part. And we also do additional clip operation here to guarantee that this Q function is always left it in the interval 0 and capital H. And after that, we define our value function as the maximum or as the maximum of the Q function over the action space. After that, we can select the action based on the Q function by greatly searching the action based on the Q function we just constructed. Okay, so here leaves a challenge here says because under the Heteroskedastic linear bandit setting, we do not need to estimate the variances here. So the one main challenge is that we want to estimate the variances here for the linear mixture MDP, which in the first glance seems very difficult. However, thanks to the following key observations, by these equations, we can see that actually the variance of the ending function here actually can be rewritten as the difference between the two linear functions. The first linear function is with the predictor of the vector phi of v squared instead of phi of v. And the second part is a square of the linear function, which is still the linear function on the phi of v vector. So because we can estimate this linear part by our original constructed hat theta h, we only need to estimate the previous linear parts, which is new to us. So to estimate this one, we again do the ridge regression approach over the predict response pair. However, here we adapt the predictor as the square of the estimated value function instead of the original linear version of the value function. That is the reason why we do that is that we try to align this estimation to this v square linear function. And after we get this solution tilde theta kh, we can build our variance estimator by simply plugging the our tilde theta and the hat theta into the previous linear function with the predictor of the phi v and the phi v square. And here, we need to do some additional clip assumption to make sure like each of these estimation is not out of the range. So we denote our variance estimator to the true variance as the bar variance of the value function vk here. So our next lemma suggests that our constructed variance estimator, the difference between our constructed variance estimator and the true variance can be upper bounded by some error bounds E. Well, I omit the details here. The only thing we need to know about E is that first things first, it is computationally efficient. And secondly, the summation of this error bounds is actually a sublinear term of the total number of episode k. So actually, as long as this term, the summation of the error bounds is sublinear, compared to the dominating term, which would be the summation of the variance, this error term would be small and negligible. So it won't play a very important role in our final regret bound. Okay, so based on the estimated variance over the value function, we can construct our final variance upper bound called the bar sigma kh, which enjoys a very similar case as it's in the hydrostatic linear bandits, where it takes constant as to guarantee that bar sigma kh is always 3 greater than 0, and it also need to takes the estimation to the variances plus the error bound here. So by now we can nearly regard this the RL on the linear mixture MDP setting as a special case or generalized case of the heteroskedastic linear bandits problem. So that indicates that we can more or less apply the result on the heteroskedastic linear bandits problem to get our final regret of the UCL VTR plus. So the result from weighted of UL suggests that the regret of the UCL VTR plus enjoys the following order. The first order comes from the R part in the weighted of UL, which is in order h squared times square root of dk. And what's interesting, the second part, well, by the weighted of UL result, we can get the d times square root of h times the summation of all the true variances of the estimated value function. Here, in order to obtain a problem independent regret bound, we further bound this term by the summation of the true value functions, which by the well-known law of total variance lemma, we can get a non-trivial improved bound in the order h squared times k. Here, if we try to apply the vanilla bound, which only yields h cubic times k, in which we cannot get satisfiable improvement. And we also get some lower terms occurring by the multiple difference sequence and the error bounds, summation of the error bounds here. So by simplifying these results, we can get the final regret bound here. So it is worth to mention, like actually our result can be extended to a special case called the problem-dependent variance bound setting, which assumes that the summation of the variances over the optimal value function can be upper bounded by some non-trivial bound, which may be smaller than the h squared of k provided by the law of total variance. The setting has been studied by Zanatti and Brunskill 2019. Okay, so our theorem.
Sorry, just a second, just to see if I'm understanding everything correctly.
Okay.
About the variance estimation that was on the previous slide. So, if I understand what happens there, I guess that happens on the previous slide, is that when estimating the variance, this V bar, then you're using the least squares estimate for theta hat, right?
Yeah,
which is from the original weighted regression problem.
Yeah, that's true.
And you're also defining this theta tilde, which is what works with these squared V features.
Yeah, that's true.
Right, and then in the end you calculate this EKH terms, and then you just add this to your estimate to have like an upper confidence bound.
Yeah, that's true.
So what is the definition of this EKH?
Simply,
I can simply spot it here.
Simply speaking, this EKH should guarantees like this: the difference between the estimated variance and the true variance can be upper bounded by itself. So I did not provide the details here, but we can see actually the EKH can be regarded as the upper bound of this linear function with this true function. And if we want to do the difference between this linear function and this function, we can see like it is essentially the difference between the tilde theta and the true theta here. And again, by providing by using the confidence radius set constructed centering at the tilde theta k, we can get actually the form of the EKH enjoys the form like the first thing is confidence radius provided by the episodic centering at the tilde theta kh, and the second part is uncertainty part, which is based on the predictor 5v square with additional matrix inverse norm, which is also based on the phi of v square, based on this new feature. So that should be the form of the EKH.
Yeah, right. But I guess this is, in the end, this is an important detail, right? Because it's not trivial that you can find an EKH.
Yeah.
That has this kind of like non-trivial form that sums up in the correct way and is computable.
Yeah. Maybe the details are in our paper. I try to save some space, so I didn't include it here. Yeah. But again,
because it's totally not trivial that this is actually a computable quantity.
Yeah, I think the non-trivial part is first things first. We need to guarantee that's the upper bound, and second thing is that we cannot apply weights probability 1 bound. We need to apply the weights hyperbolic bound, which suggests we may use some concentration inequality trick in order to get this sublinear summation of the term. That's very crucial to our final regret. Yeah.
I see. Okay, maybe later we can get back to this.
Okay, cool. Okay, so the final regrets actually can be seen in that way. So the dominant term should be square root of d squared times h cubic plus d times h to the power of 4, and with some additional constant term here. And again, there are a few remarks to mention. The first thing is that our algorithms can also be performed on another very specific setting called the time homogeneous episodic linear mixture and with a non-uniform reward MDP setting, which has been studied by the non-uniform reward MDP setting has been studied by Dan and Bronskill. And under that setting, just with a slight modified on some constants, we can get our regrets is the dominant term of our regret is in order square root of d squared plus the d times h plus times the square root of k term. And this term, recently a work by John et al. Proposed very lean algorithms, which also studied the linear mixture MDP regret minimization problem in a very different approaches. However, and they provide a dominant term, which is in order d to the power of 4.5 times square root of k. And to compare these two results, we can say that our bound has a better dependence on, and basically the nearly optimal dependence on the dimension d, but has a worse dependence on the capital H than their result. However, just as I will mention later, our algorithm is somehow computationally efficient. However, the algorithm is somehow computational inefficient or even intractable. Okay. So last thing to mention about the UCLA VTR Plus is that our algorithm is actually computationally efficient as long as we can compute this phi of v term efficiently. So to compute this term, actually this computation highly depends on what are the exact version of the features you adapted. So it's feature dependent. And for the general case, we can just do the summation over to simply do the summation over all the states in the state space. And by doing this, this would give us complexity in order of S, where S is the cardinality of state space. And to plug it back into the whole UCL VTR plus algorithm, suggests that we can perform a polynomial in the dependence of the S and A and H and K implementation to the UCL VTR plus. However, for some very specific case, well, for example, if we can factorize this phi feature by some smaller features called the psi and the mu here, actually in that case we can get a guarantee that says each of the estimated Q function we studied in the UCL VTR plus algorithms has the following parameterization form, which can be parameterized by some vector theta and some matrix theta here. Sorry, some matrix sigma here. So the only thing remain to do is to estimate this theta and sigma, and somehow if we can compute this summation efficiently by only evaluating this summation on the polynomial in the dimension of the d number of states, then we can somehow improve our complexity to the polynomial dependence of the states kinetic ace to the only dependent on the d here. So in either case, we can say that our UCLA VTL plus algorithm is computationally efficient. Yeah. Okay, so here ends our part for the UCLA VTL plus algorithm. And now we want to provide some matching lower bound to suggest that the upper bound we just studied in the UCLA VTL plus algorithms is nearly minimax optimal under some specifically and non-trivial parameter region. And to introduce our lower bound, we first consider a special hard instance for the stochastic linear bandits problem. So the speciality of this instance is due to the fact that we consider this linear bandits with a Bernoulli feedback instead of the widely studied Gaussian or the bounded feedback studied in previous work. So specifically, we suggest this agent would face the action set at each round t. The agent would select his action from the action set, which is the vertex of the d-dimensional hypercube. And the observed reward of the environment provided is generated by the Bernoulli distribution of some correction parameter delta with the linear function over the action A here. So our lemma suggests that for this special class of the so-called Bernoulli linear bandits, and for large enough k, and we can get that there exists a special linear part mu star here, which belongs to another hypercube of the d-dimensional, and for any algorithms, there should exist a mu star to let its regrets over this instance should be lower bounded by d times square root of k times delta. And to prove this lemma, we follow the standard so-called average hammer analyze strategy studied by Latimer and Szepesvari's textbook 2020. And we claim that actually the reason why we want to study this kind of Bernoulli feedback is that it provides a very precise characterization to the hard linear mixture MDP instance we want to study. And this delta we introduce is to try to balance some terms in the linear mixture MDP. Okay, so now we can introduce our hard instance for the linear mixture MDPs. So our instance can be essentially regarded as the combination of the Bernoulli linear bandits with the classical hard MDP instance studied in previous works. In detail, we provide MDP which consisting of the h+2 number of states, while the first h+1 states are the normal states which does not have any reward feedback. Only as the last observing state, the environment would provide the reward 1 at that state. And the action space is still a hypercube in the dimension of the D. And the transition dynamic here, which you can see in this figure, is that at each stage h, the agent would transit to the next normal state xh+1 with the probability delta plus this linear part dependent on the action he selected. And with the complementary probability, this agent would transit to the absorbing state and stay in the absorbing state until this episode ends. So first things we can note about this MDP is that actually this can be formalized as a linear mixture MDP by constructing the feature mapping and the linear part theta as follows. And the second thing is that actually the ultimate action the agent should select it at each stage is that it should select the action which has the same sign with the unknown linear part mu h here. And final thing is that due to the special structure of this absorbing state, due to the existence of the absorbing state, as long as this agent does not select the right action, then in the expectation, he will suffer from the in the order of H suboptimality in that episode. So these observations lead to our lemmas, which suggests that for any policy pi and with large enough k, if we select the mu h from the hypercube whose lines is in the order delta, and we choose a small delta in the order of 1 divided by capital H. So in that case, we can suggest that actually the regrets of these different, the suboptimality of this value function can be lower bounded by the H times the regret of some linear bandits, the suboptimality of some one-step suboptimality in the linear bandits problem over all the first half stages. So this equation suggests that actually learning an optimal policy over the linear mixture MDP is no harder than, or I would say it should be equal than minimizing the capital H number of linear bandits, which Bernoulli paid off. So this leads to our final theorem, suggests that there should exist a series of adversarial selected linear part mu1 to the mu h, where condition on this one, and for any algorithms, its regret will be lower bounded by the summation of the h times the summation of the capital H number of the regret things, and by our previous lower bounds on the Bernoulli pair of linear bandits, we can get this d times square root of k delta lower bounds, and by plugging this delta is in the order 1 divided by capital H, we can get the final lower bound. Okay, so to summarize, we have already get a lower bound result suggests that for any reinforcement learning algorithms, there should exist a timing homogeneous episodic mixture MDP, where its expected regret can be lower bounded by the d times h to the power of 1.5 times square root of k. And for the upper bound results, we have already shown like our UCLA VTL plus algorithm satisfies that its dominant term should be in the order square root of d squared times the h cubic plus the d times h to the power 4 times square root of k. By comparing these two results, we can see that the regret of UCLA VTL plus matches the lower bound in this parameter regime, says that d is greater than h and the absolute case number of absolute k is large enough. So we can claim that at least under this specific parameter regime, which is non-trivial, and we obtain the statistical limit d times h to the power of 1.5 times square root of k. And another thing need to mention is that our constructed lower bound is actually a valid instance for another widely studied class called the linear MDP class, studied by Yang et al. And Jin et al. Okay. Here is a simple extension, which we have already extended our result from the timing homogeneous in episodic MDP to the so-called discounted linear mixture MDP setting. So in this setting, we study a discounted linear mixture MDP, and our goal is to minimize the so-called regret measure, which is defined and studied by Liu Shu and Zhou et al. And we by applying the weighted OFL algorithms on the so-called UCLA algorithms studied in Zhou et al., we can get an improved regret bound, which is in this kind of order, where the bar h is in the order of equals to the inverse of the y minus gamma. And we also Zhou et al. Suggests that the lower bound result suggests the following lower bound result, which is in order of d times the bar h to the power of 1.5 times square root of t. And by providing this kind of two states hard instance, so we can, by comparing these two bounds, we can still claim that these two bounds are matched, which is in the region where the dimension d is greater than the inverse of the y minus gamma, and when the number of round t is big enough. Okay, so to draw a conclusion, in this work, we study the nearly minimax optimal reinforcement learning on both the episodic and discounted linear mixture MDPs. the key idea for us to get this improved result is to design a variance-dependent weighted linear regression algorithm called weighted of UL, and we apply the previous optimistic estimation strategy called optimistic estimation, and we again apply the law of total variance to get the final problem-independent regret bound. So there still remain some problems. The first thing is that can we get the nearly minimax optimal reinforcement learning algorithms for the linear MDPs? And second one is that can we obtain a linear minimax optimal horizon-free reinforcement learning, which suggests that can we either improve our dependence on the number of capital H, or can we improve another result which can improve the dimensional dependence? So these problems are still remain open. So thank you for listening.
Yeah, thank you very much. Nice. All right, so does anybody have questions? Well, I suppose I have a bunch of questions. In the meantime, the others can put it in the chat. So I had questions regarding the lower bound construction. I didn't get like how the feature map actually looks like, and what the dimensionality of this feature map is. Maybe I'm just not getting what these alpha, beta, delta parameters are. Can you explain?
Oh, okay. So actually, in here, this alpha, beta are simply scalars. These things are provided to satisfy the bounded assumption. Since we will actually study a general class where we assume that the feature mapping phi can be bounded by some greater than one constant b. So we want, in order to satisfy this constraint, we need to introduce two additional parameters, is alpha and beta, and to try to renormalize this vector to let it always be upper bounded by capital B. So as you can see, the dimension of this feature mapping is D, because this A enjoys the dimension D minus 1, and this 1 minus delta is only a scalar. So by calculating these two things together, we get a D-dimensional feature mapping here.
Right. Now I'm just trying to read the dimensionality again. So like A is D-dimensional, or like D minus 1 dimensional?
Yeah.
Oh, I see. Okay, no, I was just looking at all those cases, and I thought that all these things are concatenated, but no, these are separate cases for the feature map.
Yeah. They are concatenated.
Right, but then you said that this bound holds for general B, or general capital B, but how does that show up in the lower bound? I didn't see that.
That's another thing I did not emphasize in this slide. So we actually prove that for any b greater than 1, then we can get the lower bound in this order, which actually is independent of b here.
Yeah, I imagine. Yeah,
and
because B is supposed to be lower bounded by 1, so.
Yeah, and the importance of this thing is that we actually prove that no matter what kind of capital B it is, it is easy to imagination says when B is greater, then this problem should be harder than, and when B is smaller, then this problem should be easier. And we just prove that this lower bound says that no matter, as long as this B has constant lower bound, then for any algorithms, they can learn this MDP in this norm-independent fashion.
Okay, I'm not sure I'm following. So like, what would an upper bound look like? So if you would use a algorithm with in a setting where B is greater than 1, what is the upper bound that you would be getting?
For the B.
Oh yeah, I see. Yeah.
Yeah, B is greater than 1. This regret still holds.
So B doesn't even appear in the lower order terms?
It actually should be appearing on logarithm term, which I'll meet in this tilde notation.
Oh, I see.
Yeah. So basically speaking is that actually our algorithms can learn this with the regret only dependent on the norm B logarithms.
Right. Yeah. I can see that, and that comes from the covering number.
Yeah. That's true.
Okay, and what about this condition that D should be greater than H? Can you talk about it a little bit more? Like, is this realistic? Is the other case interesting at all?
So it depends on what kind of case you are interested in. So if in the very special cases, we just consider this D is upper bounded by a square of A, but also has some lower bounds, and I think it is non-trivial for us to study the regime where the dimension D is great. However, if you are interested in another regime, says the dimension D is much smaller, says like a constant, and then our upper bound still holds. But as you can see, the dominant term should be switched from the D to the D times H to the power of 1.5. It should be switched to the square root of D times H square here. And it somehow does not, we cannot say it does not match a lower bound, but it seems to suggest that the dominant term, then looking at the fashion here, it does not match a lower bound. But for under that, at least in that region, we can say the both of them has a very simplified representations. It's in the order D times H to the power of 4.5 times square root of K. Yeah.
Right, I see. Nice. And then, like, regarding this this algorithm construction,
okay,
that you have. So, is this? I imagine that to a degree, this is probably inspired by this previous paper by Azar, Osband, and Munoz, no? Where they use like Bernstein-style exploration bonuses for tabular MDPs.
Yeah. It has been motivated by the previous, including the Azar et al. And many previous existing near optimal results on the tabular MDPs. And nearly all of them, actually all of them should take the use of the Bernstein type of multi-code inequality. That's a very key step for them to achieve the near optimal regret.
Yeah, but can you remind me of the variance estimates that were used in those earlier papers? Was it not just like a plug-in estimate, or did they also have to do this kind of fancy thing that you needed in the end, this theta tilde estimation and then this bonus?
Actually, they all of them need to estimate the variance, need to construct this kind of variance estimator. They need to construct this kind of variance estimator. And I would say the formulation of the Bernstein type bonus is that since they are considering the tabular case, so they are very, very similar to the multi-arm bandits. And for the multi-arm bandits, you always can get a bonus in the form of the square root of n, with the variance as the variance divided by the square root of n. So their bonus is in the form of the variance divided by square root of n. But in our case, since it is hard for us to get an independent variance estimator, so we cannot get the square root of n just as in the multi-arm bandits explicitly. In contrast, we just build, as you just suggested, this kind of plug-in estimator, which would based on what kind of action you select and what kind of variance you just estimate. So that's the difference between the. Actually, that should be the difference between the multi-arm bandit case and the linear bandit case. This difference contributes the difference between our algorithms and the previous near optimal tabular MDP algorithms.
Right. So in the end, would you say that the difference, like the key idea here, is the introduction of this EKH term that you add to the variance estimator, but or the introduction of this theta tilde?
Actually, I would say these error bounds is not as important as the tilde theta here.
I see.
So
I see.
this error term again is a very small, or you can say call them a correction term. So this order actually this contributes a negligible order in the final regret, since we can get the summation of the error is the sublinear term of the k here. The dominant term is the summation of the actually the summation of the estimated variance, and then we get one step to get it from the estimated variance to the true variance, and again one step we get it to apply total variance lemma. So yeah.
So you say that this is a minor term. The sum of these e's is minor because this appears under another square root in the end?
Yeah, there exists the square root of k here.
Yeah, but that is of the order of the final bound. So you're saying that, well, this square root of k times d to the 3/2 times h cubed, so this goes under another square root in the end? So in the order, this is like k to the 1/4?
Actually, as you can see, the summation of the variances the square root of 1. So actually, if we directly bring this summation of the EKH to our regret, actually it contributes k to a power of 0.25 instead of square root of k. So that's again a low order term. Yeah.
Right. Yeah, that's exactly what I was wondering about. Okay. That's great. Very nice. Right, so I'm just wondering if anybody else had a question. Johannes had some questions. I don't know if those are answered. Johannes, are you still around?
Yes, hi. Thanks for the talk. I was wondering about why you're using a heteroskedastic variance bound and not a sub-Gaussian bound, like a heteroskedastic sub-Gaussian bound. Would there be a difference in the results? Like, are you exploiting the gap between the variance bound and the sub-Gaussian bound?
Okay. If you are directly using the sub-Gaussian bound for the Heteroskedastic linear bandits, I guess it can provide you the regret in order says the d times square root of summation of the RT square instead of sigma t square. If you are suggesting to using the sub-Gaussian bound and a heteroskedastic linear band setting, but it cannot provide us a summation of the sigma t here.
Okay, so yeah, I agree. Would that make a difference for the MDP setting?
I think so, because in the MDP setting, again, we treat the original problem as the linear bandits problem with this kind of predictor and response. And if you want to get a sub-Gaussian norm over this random variable, I would say you can only hope for boundedness for a magnitude bound, because the sub-Gaussian bound should be always greater should be in the same order of the magnitudes if you are facing a bounded variable, right? So in that case, you can only adapt the h. You can only adapt the sub-Gaussian bound for this v, and maybe in the end you can get a regret bound, which is the summation of the sub-Gaussian norm of this value function. But again, this part cannot get some relation with the law of total variance lemma, because the law of total variance lemma should be dealt with the summation of the variance, but not the sub-Gaussian norm.
Okay, that makes sense. Thank you.
Yeah, that's also the key reason why we want to study the variance-based algorithms instead of the sub-Gaussian norm-based algorithms.
Yeah, I think that this is a good question. Like, well, yeah, we know that, well, the variance accumulates at a certain rate due to this law of total variance. But do you know for sure that something similar does not hold for the sub-Gaussian constant? So, like, is there a known counterexample that shows that, well, the sub-Gaussian constant actually has to rack up faster than this?
I would say, like, if you are facing a more restricted function class, says like the problem setting studied by Zanetti and Brunskill, they try to give the summation of the variance another bound which is smaller than the bound provided by law of total variance lemma. If you are trying to study the setting, well, you assume the summation of the sub-Gaussian norm of the value function can be upbounded by some another constant, then I agree that we do not need to utilize our improved Bernstein type of inequality. You can only adapt the weighted strategy, and I guess you can get the final regret bound, which is dependent on the summation of the sub-Gaussian norm. But again, if you want to get a bound which is dependent on the summation of the variance, then I guess the Bernstein thing is that thing you need. Yeah.
Yeah, and anyhow, it feels pretty hopeless to try to estimate the sub-Gaussian constant.
Yeah.